Proflan YouTube channel. In this particular video, we're going to have a discussion on how to work out questions involving the topics materials. So we're going to look at strain, stress, and Young's modulus. We shall have a detailed discussion on what are the key areas that you must focus as far as your A-level AS Mechanical and Materials Unit 1 exam is concerned. If you are new to Proflan YouTube channel, consider subscribing so that anytime we are going to upload another tutorial, you'll be notified. Now we need to begin and look at the first question, whereby we are told a steadily increasing tensile force was applied to a sample of titanium alloy. The sample had the original length of 4 centimeters and diameter of 5.05 millimeters. And we are supposed to state the suitable instrument to measure the diameter of a sample. Remember, the choice of an instrument depends on the nature of the measurement that has to be taken. Now, for instance, if you want to measure thickness of a sheet of paper, thickness of a thin wire, thickness of a thread, thickness of hair, you can use a micrometer screw gauge. And you need also to know which instrument should be used to measure maybe the inner radius of a measuring cylinder. That one is a vernier caliper. So this one we're going to use a micrometer screw gauge. Now the graph shows stress varies with strain for a sample, where you're going to meet various questions which involve that. And you need to understand when a graph is drawn stress against strain, you are going to have a section where is a straight line. So in that straight line, it means that in this region where it's a straight line, it means that stress is directly proportional to strain. And you can be able to use this straight line region in order to work out the value of the Young's modulus of the material that was used to come up with the graph. Now let us see into and determine the Young's modulus of the sample. You are given, if you be given in your exam a graph and then you are supposed to work out the Young's modulus, you are going to work out the gradient of the section where the graph is straight. You need to find the gradient of the straight line graph section when you are told to work out the Young's modulus. So we are going to work out the gradient in the section whereby we are going to draw a right angle triangle, then we find rise and run. So our rise is actually 800 times 10 raised to the power 6, and run, we can be able to understand the scale that is used here, and then we can be able now to work out the gradient. So working out the gradient, we are going to get a value equivalent to what? Let us see what we're getting. We can be able to use our calculator, and then our value becomes, let me see, 1.2 times 10 raised to the power 11 pascals. Remember, the unit for Young's modulus is pascals, because you are dividing stress divided by strain. The unit for stress is pascals or Newton per meter square, but strain has no units. So that is why we are saying the Young's modulus has got the units pascals. Pascals just like pressure, right? Now, something else that you need to remember is that Young's modulus tells you how stiff a material is. Those materials which are quite stiff, which are very stiff, they have a large Young's modulus, meaning that it will be very difficult for you to bend such kind of materials. Metals have a large Young's modulus than materials which easily bend, so that's quite important. And this is a concept, that this is a property of material which is used by engineers in order to know whether a material that is used or a metal that is used in a given building is able to withstand different forces. We need to move down and determine the force required to break the sample. We can see the information provided. We have the Young's modulus. So now at B is the breaking point. Yeah, B is the maximum force that can be applied in order to break this object. Then we can be able to check what is the stress at point P, the stress which correspond to B. Then now, once we have that stress, we can be able to use the concept of stress, having the fact that stress is equals to force over the cross-section area. So the stress in this case is 1290 times 10 raised to power 6 pascals. And then we can be able to go now down here and say stress equals to force over area. Right, so we can be able to check here. We have the original length and we have the diameter. Now this diameter that we have, which is 5.05 millimeters, can be converted to meters, and then it's going to enable us to work out the area, and which is the cross-section area, because when you are working out pressure, you need to know what the cross-section area is. So we're going to use 5.05 millimeters. We work out the cross-section area. So diameter is given in millimeters. Then we can be able to convert this by multiplying by 10 raised to power negative 3, and that becomes now in meters. Then once we have that, we can be able to find the area of the cross-section of the cross-section area of that wire, of that sample. Then we can be able to use the formula pi r squared. Then we will have to divide by 2 so that the diameter can be converted to radius. So working out this, we are going to get what? Let's use our calculator here. (2.0 times 10 raised to power negative 5 meter square), which will mean that we can now use this area we have gotten together with the stress that is here. We can now be able to work out the force required to break this sample. Then we can now say force equals to stress times cross-section area, because if you rearrange that, force will be equal to stress times cross-section area, meaning that we can now multiply that cross-section area together with the stress. Then we can get our force being equal to 2580 newtons. 2580 newtons. Our force becomes 2.58 times 10 raised to power 4 newtons, and that is exactly what we are going to write down here, just to make the examiner happy. If you are new to Proflan YouTube channel, consider subscribing so that anytime we are going to upload another tutorial, you'll be notified. Moving down, the graph shows a linear section of a stress strain graph for the sample, and then we are told that show that the area under the graph represent the work done per unit volume of the stretching object. Now first we know that area of this is actually a half base times height. So we can be able to say now area is equals to a half base times height, but our base is going to be the strain and our height is going to be the stress. Yeah. So writing this in the strain, we know strain is calculated by the formula extension over the original length. Yeah, I can be able to write that epsilon times sigma. Of course, those are the symbols for strain and stress, but we know that strain is extension of original length, and sigma, which is stress, is force over area. If you multiply E times F, just work done is equal to E a half EF. Remember, work done in a spring is a half times extension times the force applied This is the section for work done. And then we know that length times cross-section area gives us volume. It gives us volume. Then you can be able to say therefore area is equals to work done over volume, like that. So this is just a proof that the area represents the work done per unit volume. Now, working at Roman form, we are told that the area under n stress strain graph represent the work done per unit volume. Estimate the amount of work required to break the titanium alloy sample. So meaning that we can now go back and work out the area of one square. We need to work out the area of one square, so that once we know the area of one square, we can go ahead and work out the area under that graph, so that we can be able to find the area under the graph. Then we shall now say that that area is equivalent to the work done per unit volume. So using the scale, the area of this big square is actually going to be 100 times 10 raised to the power 6 times 0.005, and then if you work it out, you're going to get 5.0 times 10 raised to the power 5. Then once you have the area of one square, you can now go back to this, because the breaking point is at B. So we're going to work out the area under the graph from the beginning to where B is. So we're going to use counting the square. We count all the, in order to work out this, we're going to count all the complete squares under the graph and then count those incomplete squares. Now to work out the area under the graph using estimation of squares, we usually say is the number of complete squares plus a half of all the number of the incomplete. Then now once we have done that, we are going to multiply each of the incomplete, and this now will give us incomplete squares. We count all incomplete squares. Then now we shall add the number you have for all the incomplete squares times a half, and you add the squares. Then from there you shall now say this is, of course I've counted the complete squares are 1 or 2, incomplete squares are 33, then 33 divided by 2, then we add now the answer we get. Now I've gotten out the area, and the number of squares below the graph is 118.5, then times the area of one square, which is going to be what? Let us work it out using a calculator and see what we are going to get. .925 times 10 raised to power 7 joules per meter cubic. Now we have the area under the graph, but we know we need to work out the, let's see, we have the length and we have the cross section. Then we can be able to work out the volume. Volume is cross section area times length, which we are going to substitute the values we have. And remember also to convert the units to meters. So the volume is 8.01 times 10 to the power negative 6, but area now is equals to work done over volume. Then to calculate work done, it will be volume times area, which means that we are going to take area, which is 5.925 times 10 raised to the power 7 times now the volume, which is 8.01 times 10 raised to the power negative 6. Working out this, we're going to get our value as this 4 point. We're going to get 474.6 joules, which is 4.7 times 10 raised power 2 joules. Now this is the work done to ensure that titanium alloy sample is broken. In question 2, the diagram shows a climber on a rock face. A rope is kept firmly anchored by a person on the ground and passes through a smooth loop over the climber. The climber slips and falls a short distance as shown. Yeah. The fall factor is used by climbers to estimate the severity of a climbing fall and is given by fall factor equal to height fallen before the rope begin to stretch over the total unstretched length of the rope. A climber slips and fall through a fall factor of 0.8 before coming to rest. Then we are told that the maximum strain in the rope is 9.0%. We are told that the maximum strain in the rope is 9.0%. Remember, strain is non. Remember, strain doesn't have units, so it can also be expressed as a percentage. Strain has no unit, it can be expressed as a percentage. Show that the maximum force acting on the climber due to the rope is about 10 kilonewton. Assume the extension of the rope is proportional to its tension. Total unstretched length of the rope is 15 meters. Now, the first thing we're going to do is to use the fall factor. And using the fall factor, we can be able to work out the height fallen by the climber in the process of that. So we have the unstretched length is 15, so we can be able to use the factor to get the height that climber is going to fall through. Now, working out that, we are going to get the height is 12 meters. Now, number 2, we need to go down here. We know that strain is equals to extension divided by the original length. But we had said that strain has no units, and it also, because it's a ratio between two lengths, it can be also expressed as a percentage. So we can be able to use that information in order to work out the extension. So we can say 15 times 9 over 100, 9% of that. So that translates to 1.35 meters. And then we can now be able to say that gravitational potential energy, because once this person is going to fall to some height, there is a change in energy. So there is gravitational potential energy which can be obtained from the mass and the height fallen of 12 meters, and we can get that to be equivalent to 8,358.12 joules. But there is also potential energy due to the extension of this rope, and this is going to be what? This is mass times gravity times the height, or the length fallen, which is 1.35. So from the fall GPE due to the extension also is going to be that. And remember, now these two gravitational potential energies will be added together, and that energy, now we have gravitational potential energy, is going to be transferred into the stretching rope, and that now remembering that the climber was at this given point, then immediately this person's slips is going to fall through a given height. So meaning gravitational potential energy will be converted to elastic potential energy in the rope. So that's why we're saying that in that process, in order to work out, because we're supposed to show that the maximum force acting on the climber due to the rope is 10 kilonewtons. Is approximately 10 kilonewtons. So, which means that we can work out the potential energy due to the falling height of 12 meters, and also we work out the potential energy due to the extension of the rope of 1.35 meters. Then we add the two, but we shall now say that energy is equivalent to a half force times extension, right? So meaning that we're going to work out this value of F, and which is going to be approximately 13.7 kilonewtons. This is 13.8 kilonewtons, which is approximately 10 kilonewtons. Gravitational potential energy, the concept used here is that gravitational potential energy will be converted to elastic potential energy. Explain how the work done to break the new cable is different from the work done to break the original cable. Now, replacing the original cable with a lower Young's modulus, it means the new cable is more elastic. This means it will stretch. Let me just write this properly here. It will stretch more under the same stress, compared to the original cable. The two cables have the same breaking stress. That information was given. Then the new cable has a greater diameter. Since the new cable has the greater diameter, this results to a large cross-section area. And then we can now say this allows the cable to withstand a large force before breaking. So the work done to break the new cable is greater than the work done to break the original cable. Climbing rope manufacturers recommend that ropes are replaced every 5 years. The force extension graphs up to the breaking point for a 1 meter length of a rope when new and after 5 years are shown. Then we have the graphs here. We are supposed to comment the manufacturer's recommendation. You can also we are going to include calculations involving, in order to explain this, we're going to use calculations. Your answer should include calculations. So we know that area under the graph, force against extension, gives the energy or the amount of elastic potential energy stored in that material. So meaning in order to show this, we're going to work out the area under the graph for the rope when new and also for the rope when after 5 years. Then we see which one has more energy, which one can be able to store more elastic energy. So if a material stores less elastic energy before breaking, then it's going to be what? It's going to be dangerous, because that rope or that material is going to snap or break immediately a small amount of energy, a small amount of stretching force has been applied. So in this case, we're going to say that area under a graph represent the elastic potential energy that is stored in that material. So meaning that for the new rope, you are going to count the number of squares below the graph, and then find the area of one square, count all the squares, and then find the area of one square, then multiply by that in order to work out the area under the graph. So we can be able to subdivide this and then count the number of squares. So first let's find the area of one big square. So if you work out the area of one square, you can see now that is 2500 by 0.025. Then the area is going to translate to what? The area becomes 62.5 joules. So then now we're going to count the number of squares below the new rope. Once you get the number of squares, then you can be able to multiply by the energy stored by one square, which is 62.5. You do the same for the rope after 5 years, and then you're going to realize that if you do the same, you're going to get different values. Energy stored in the new rope is going to be approximately 800. You're going to do that and check whether you're gonna get that. And energy stored in the old rope is approximately 700 joules. So you realize that the energy now stored in the new one is more than the old one. So meaning that if you apply a small amount of force on the old one, it's likely to break. So that is why the manufacturers were able to recommend that. So you have also to comment on that so that we can be able to say old rope is not stiff enough as stored energy is less, and this will break at a small applied force. In question number 3, when an increasing force is applied to a steel cable, it will eventually reach its elastic limit. Now we are supposed to state what's meant by the term elastic limit. Remember, materials, when stretching force or when tensile force is applied on materials, they increase size. So as the size increases, it will reach a point whereby if you add a force that is beyond a given limit, the material will undergo plastic deformation, which means that the material cannot be able to regain the original size and shape upon removing of that stretching force. Now, elastic limit is the maximum force a material can withstand, beyond which that material undergoes plastic deformation or deforms permanently. So we can be able to say here that is a force, or is this is a force beyond which a cable does not return to its original length when the force or the stretching force is removed. Right? You can give different definition on this, but this is the simplest one. That is a force beyond which the cable does not return to its original length when the force is removed. We can also say is the force beyond which the cable undergoes plastic deformation. So which means that at this point also you need to understand what we mean elastic deformation. Elastic materials are materials which can increase in size and then go, materials are said to be elastic because they can increase in size when a tensile force is applied, but they can regain their size, original size, when that tensile force is removed. So plastic deformation is a deformation where a material can regain its original shape once that force is removed. But plastic deformation is a deformation where the material cannot regain the original shape or size once that force is withdrawn. So you need to understand those terms. So there's another point also we're gonna mention about the proportional uh, just becoming too much. The elastic limit of steel cable was reached when a force of 13.4 times 10 raised to power 6 Newton was applied. The extension of the cable was 0.126 meters. Length of the cable is 6 meters. Cross-section area of the cable is 9.60 times 10 raised to power negative 3 square meter square. Calculate the strain and of the cable at its elastic limit. Strain is equal to extension over strain is equal to extension over the original length. So meaning that we can be able to work out strain, which is going to be delta x, which is the extension over the original length. So we can be able to substitute the values here and then say our extension was 0.126 divided by the length, which is 6. Then working it out, we're going to get our value equivalent to 0.021. And remember, strain has no units, it's dimensionless. So it has no units because it's a ratio between two lengths. So strain, you're gonna realize sometimes it can be given as a ratio, it can be expressed as decimals, but there are no units, and sometimes it can be given as a percentage. So we can be able to say our strain is 0.021. We're supposed to work out stress of the cable, and the stress actually is force over cross-section area, and stress is the force that is developed within a material when tensile force is exerted. When you stretch a material, when you stretch, you apply a force to stretch a material, then the force which is internally developed to resist this force that you are trying to cause, you are trying to put in on the material, is called stress. So when you apply a force over a given area, then we have that particular value, that quantity we call what? Stress. And stress determines if materials can break. Yeah, some materials have withstand large amount of forces for them to break, and some materials can break within a given small force that's applied to it. Yeah, so let's see here. We can be able, first we are supposed to work out stress, and we have said stress is a force developed in a material when you try to stretch it or compress it, and this is going to be 13.4 times 10 raised to power 6 divided by the cross-section area, which was 9.6 times 10 raised to power negative 3. Working it out, we're going to get our answer being equivalent to what? Let's work it out. 1.396 times 10 raised to power 9 pascals, because this unit, pascals, just as the unit for pressure, but you see, for us to work out stress, we're dividing force and area. Force is in Newton and the area is in meter square. So other units for stress are Newton per meter square, just like pressure. Okay, so that is it. We have our pressure calculated. We need to move to question number 4. We are told an engineer is designing a metal part of the machine, and the part is in the form of a cylindrical rod. The part is designed to behave elastically when compressive forces are applied. So you see now, if you apply compressive forces, the size of this rod is going to decrease, but that rod is going to exert external forces to try to resist the forces that are being, the compressive forces that are being exerted. But in part A, we are told to state what's meant by elastic deformation. We have mentioned in our previous discussion that elastic deformation is a deformation which occurs and a material can be able to regain the original size when the force is withdrawn or removed. So we have two types of deformation: plastic deformation, which is permanent. Once a material undergoes plastic deformation, it cannot regain its original size and shape. But for plastic, for elastic deformation, a material regains its size once the tensile force is removed. So we need to write a precise definition of what is meant by elastic deformation. And we're going to say here that we're going to say here that we're going to say that in elastic deformation, a material returns to its original size and shape when the stress or the tensile force is removed. That is basically what you are supposed to state in this question. Now, next, we are moving to part B, whereby we are told a compressive stress strain graph for one metal is shown here. For one metal is shown here. We have on the y-axis, we have stress, and on the x-axis, we have strain. Then we are supposed to do what? Let's see. What are we expected to work out? Show that the Young's modulus for this metal is about 2 times 10 raised power 11 pascals. So basically, the examiner is trying to test whether you understand how to get the Young's modulus from a stress and a strain graphs. But since you've watched a tutorial from Proflan YouTube channel, you have been told that from stress strain graphs, for you to get the Young's modulus, you need to work out the gradient of the straight section of that particular graph. So we're going to say the gradient of the straight section of the stress strain graph is going to give us the Young's modulus. So we can say change in stress over change in strain is going to give us the Young's modulus. Then we're going now to go to our graph here. Then we can be able to identify a section here and try to see what's the reading down here and what the reading on the top here. If we go across, what will be the corresponding stress at this point? Then now we can now pick it and check. This is 44.45, and then we can also identify the strain down here so that we can be able to work out the gradient. The strain down here is 2.125, and then we can be able, don't forget there was times 10 raised power 8 there. That is an area that you have to be very careful. And then we write this value times 10 raised power negative 3 and work out now your value using your calculator in order to see exactly what is expected of us, which translates to 2.09 times 10 raised power 11. And you can see it's approximately this value that we were given at this given point. I believe that is okay. We can now move to the next question in Roman 2. And in Roman 2, we are told the metal part must not compress more than 0.6 millimeters when a force of 9.5 times 10 to the power 5 is applied. That's the condition. Then we're supposed to deduce whether this metal is suitable for the part. Yeah. the metal length is 0.84 meters and the cross-section area is 4.8 times 10 raised power negative 3. Now, something that I need to mention here is that Young's modulus is does not depend on the dimensions of the section of the material. Young's modulus is a property of a material. If you have a piece of metal from a given material and you get another piece of a different size from the same material, if you work out the Young's modulus, you're going to get the same value. So we can be able now to use the information provided here and check whether is the extension is the compression equivalent to 0, is it more than 0.6 or is it less than 0.6. If it's more than 0.6 millimeters, then we're going to say that material is not suitable. That metal is not suitable for that part. So let us now begin. Let's begin working out this question. We know that force that was given here was 9.5 times 10 raised to power 5 Newton. Length was given as 0.84 meters. Cross-section area was given as 4.8 times 10 raised power negative 3, right? We have Young's modulus, we had obtained it, so we are going to use the Young's modulus that we have gotten from the other previous section. We can say, let's use the Young's modulus that is there. 2.09 times 10 to the power 11 pascals, and our objective is to find delta x. And this delta x that we shall find, which is the extension, we shall compare it with the 0.60 millimeters that we have somewhere there. So stress can be obtained from the formula force over area, and we have the force, we have the cross-section area, then we can be able to get the stress is equivalent to what? Let's see, 1.98 times 10 to the power 8 pascals. And then we can now say Young's modulus. Young's modulus is stress over strain, which implies that we can be able to work out strain from the formula. Strain is equals to Young's modulus. Strain is equals to Young's modulus. Strain is equals to stress over the value of Young's modulus. So working it out, we're going to get our strain equivalent to 9.47 times 10 raised to power, let's see, the power 4. Yeah, so now using the strain that we have and the original length that we were given 0.84, we can be able to work out the delta x. Can be able to work out the delta x. So you can say delta x over L is equals to strain, but already we have the strain. So we can be able to say delta x is strain times the length, original length of the part that we were told, and that is going to translate to 0. What? Working it out, we're going to get 0.7. Let me see. No, in meters it's going to be 7.96 times 10 raised to power 4 meters. But you can now convert that to millimeters. We can convert this to millimeters by dividing by 1,000, which translates to 0.79 millimeters. So we can now see that 0.796 millimeters is more than 0.6. Then we can say now the material, the part, that part is not suitable. It's not suitable because 0.796 millimeters is greater than 0.6 millimeters. So meaning that it's not suitable. It's not suitable. Not suitable. Not suitable. Since it compresses more than 0.60 millimeters. A student carries out an experiment to determine the Young's modulus of copper. She uses the apparatus below to observe the position of a marker as a copper wire extends under increasing applied loads. We are supposed to describe how the diameter of the wire will have been determined. Remember, diameter of a wire can be determined using the micrometer screw gauge. But in this question, we are supposed to describe. So meaning we are going to measure the diameter in different orientation, in different positions along that wire, and then we get different values of which we are going to add them, divide by the number of values that we have taken, meaning we work out the mean or the average of the data taken for accuracy. When you are told to describe, that's what you are supposed to do. So we were supposed to state the instrument. First, we were supposed to state the instrument of measurement, and we are going to say using a micrometer screw gauge. Then we are going to explain further and say measure the diameter in different sections and in different position and different orientation along the wire. Thereafter, we shall find the mean average, the mean value of the diameter for accuracy. Still, we have another question here whereby we are told the student calculated the extension of the copper wire for each applied load, and she then plotted a graph against extension. Right, so we are supposed to determine the value of the Young's modulus of copper if the original length of copper was 2.4 meters. Yeah, 2.4 meters. And also we were given the diameter there. But for us to do that, we know that the diameter of copper is 2.3 times 10 to the power negative 4 meters. So the first thing that we ought to do is what? Is to work out the gradient of the straight section of this graph so that we can be able to work out the spring constant or the Now, first we are going to work out the area of the cross section of the wire, and then using the information, remember the diameter was given there, but for you to work out area, you need the radius. So that's why we are dividing by 2. Working out, we are going to get our value as all right. So next, we are going to work out the gradient using the straight section so that we can be able to work out the constant of proportionality. Yeah, the section where the graph is straight. But if it was a spring, we were to say we are working out the spring constant. But in this case, we are using a wire. We'll say we are finding the constant of proportionality in that case. So the gradient is going to be that. So our gradient is actually going to be what? 6.5 divided by 2 times 10, 2.9 times 10 raised to the power negative 3. The gradient is going to be in Newton per meters. In Newton per meter. So meaning you have the force per a given force that extend this wire in 1 meter. The constant of proportionality that we have obtained is telling us if you apply a force of 2.2 times 10 raised to power 3 Newton, it is going to extend this wire by 1 meter. So extension is 1 meter. Then we can now be able to use this information in order to work out what? In order to work out the Young's modulus. So this is what that constant of proportionality is telling us, that a force of 2.2 times 10 to the power 3 provides an extension of 1 meter. So meaning from this information, we can be able to, since we know even the area, we can be able to work out the stress, and we can also be able to work out strain. We already know the length of the wire. Yeah. We know the diameter of the wire, which enabled us to work out the area. We have the force that produces an extension of 1 meter, then we can be able to use this information in order to work out Young's modulus. All right. However, let me just take you a different section. Young's modulus is can also be calculated from okay, this is strain. Strain is going to be that, which is going to be 1 over 2.4 because extension is 1, but the length, original length of the wire was 2.4. Then stress is going to be given as force over area, and we know the force we shall use is 2.2 times 10 raised to the power 3 divided by the area, and the area we have 4.1515. This is 1 here. This is 1 here. Then now we know Young's modulus E is equals to stress over strain. Our stress, we have it as 2.2 times 10 raised to the power 3 over 4.15 times 10 raised to the power -8. Everything divided by the strain, which is 1 over 2.4. So working it out, this is going to reduce to what? This is going to reduce to, okay, that was just a reminder that Young's modulus is that. Young's modulus is stress over strain. Now let's go down here and try to work out what's the final answer for that using our calculator. Yeah, 1.27 times 10 raised to the power 11 pascals. Explain why the sum of wire used in the experiments should be long and thin. Remember, if you have a long wire, it will provide a larger extension over a small force that is applied. If you have a thin wire as well, it will stretch more compared if you are having a thick wire, which requires a lot of tensile force for its tensile stress for it to stretch. So basically we are going to base our answers around that. Longer wires, a longer wire allows for a noticeable extension when a force is applied. This makes it easier to measure small changes in length accurately. Thin wire, with a thin wire, a small force is required to attain a noticeable extension, and this ensures the material remains within the elastic limit. Because if you add a large force, the material may go beyond the elastic limit. So we need to be adding small masses. We can be able to monitor the extensions and then later use them in order to come up with a graph. Right. So this aspect is also going to reduce the errors in the experiment with thin and long wire. We notice that the uncertainty of the extension is going to be lower, and then that improves the experiment. That improves the experiment. Right, moving to the next question. Can add a statement and say small load can be used if you are using a short and thick wire. You need big loads in order to observe some extension, but in this case we can be able to measure and determine different extensions with just small loads. In question number 7, a student carries out an experiment to determine Young's modulus of copper. She added a mass M to the free end of a sum of copper in the form of a long wire, thin wire, and the corresponding extension delta X was measured. This was repeated for increasing masses. We're supposed to state the meaning of the term Young's modulus. Young's modulus is a ratio between the stress and strain of a material. Is the ratio of stress to strain for a material. Remember, we had mentioned the formula for Young's modulus, and that's where we're getting that definition from. And we also mentioned that the value of Young's modulus determines how stiff a material is. Those materials which have a large value of Young's modulus, they are very, very stiff. They cannot bend easily. Determine the cross-section area of the sample, and we are given different diameters of that samples of different sections. So for you to work out that for accuracy, first we need to work out the mean of the diameters, and then once we have the mean, we can be able to use the mean of the diameter obtained, divide by 2 to get what? To get the radius. But now, since we have 4 samples, we are going to divide here by 4, and this is going to translate to 0. What? Shall say 0.234, around 0.234 there. And then we can now go ahead, say area equals to pi d over 2 squared. Then we can be able to substitute the values, and we shall get our area being equivalent to 4.3 times 10 raised to the power -8 meters square as the area of the sample. Now, the student plotted a graph of M against extension. She measured the gradient and observed the value of the gradient is 195 kilogram per meter. So here, what you need to understand is that mass is proportional to weight. So it's going to have the same graph if we had plotted a graph of force against extension. So graph of M against extension is the same graph because mass and weight are proportional. You need also to remember that weight equals to mass times gravity, so that we can be able to convert that that constant of proportionality to Newton per meter. Yeah, so that we can be able to convert that will be equal to 195 times 9.81, which translates to 12.95 Newton. So we can say the value of the gradient can be written as 1912.95 Newton per meter. And once we have this, we're supposed to use this information to work out the Young's modulus. So taking the constant of proportionality times the original length, which is 3.5, of the cross-section area, it will give us the Young's modulus. This is something that you need to remember. If there's a relationship between Hooke's law, stress, strain, and the Young's modulus. So if you take the spring constant times the length of the spring divided by the cross-section area, that will give you the Young's modulus of that material. Alternatively, I can also show you that using the constant of proportionality, we'll know, that is method 2. We know from the constant of proportionality that a force of 1912.95 will give us an extension of 1 meter. So we can be able to say, using that information, and then we convert that mass to kg, we shall have this Newton will give us an extension delta x of 1 meter, yeah, from the constant of proportionality. But now, since we know the cross-section area and also we have the length, we can be able to work out the stress of this material using force over area. And our force is stress is equals to 1912.95 divided by the area. We shall get the stress like that, like that. We shall have the stress here. Pascals. Now, using the delta x and the length of 3.5, we can also work out the strain. But remember, Young's modulus is equals to stress over strain. Then we can be able to substitute those values that we have there so that we can be able to work out the Young's modulus. And if you work it out, you are going to get it's the same as 1.6 times 10 raised power 11 pascals, the way we got it on the other end. Now, in the experiment, the experiment was repeated by another student using 2.00 meter length of copper wire. Now we are told that suggest how the value obtained for the gradient, hence suggest how the values obtained for the gradient, and hence the Young's modulus will differ between these two students. Then we need to understand that a shorter wire will give a larger gradient, give a greater gradient, because with a shorter wire, we are going to have a small strain, yeah, because strain is delta x over the original length, but the original length now is going to be the wire is going to be 2, which is going to be shorter. So that's why we are saying a shorter wire will give a greater gradient. However, the Young's modulus is going to be the same because Young's modulus does not depend on the dimensions or does not depend on the length of the piece or what. It's just a property of the material. So long as the materials are the same, then the Young's modulus is going to be the same. So we have another question here whereby the actor is suspended using a harness and a cable which supports this person to hang like that. Now, the force on the cable must not cause the material of the cable to reach its yield point. State what's meant by the point, the yield point of a material. Now, if you look at the stress strain graphs, we have different sections. The first section is A, whereby A is the proportional limit of proportionality. From O to A, the material behave in such a way that stress is proportional to strain. So this is the region whereby we say even the material obeys Hooke's law. So from O to A, the stress is proportional to strain. So you can be able to use that region in order to work out the Young's modulus from the gradient. We have another point B, which is called the elastic limit, or it's called the yield point. This is the point, or this is the maximum stress beyond which an additional stress can cause this material to undergo plastic deformation, meaning the material can be deformed permanently. C is a lower yield point. We have breaking stress, which is D, which is the maximum stress and a material can be able to withstand, beyond which the material is going to break or fracture. So something else I need to mention here is that you can see D to E. if the distance from D to E is too short, it means from the maximum force this material can withstand for it to break. If the distance between E and D is small, it means this material is brittle. It can easily break once you've exceeded, once you exceed slightly beyond the breaking stress, yeah, which is the ultimate breaking stress. So we have also other materials which are called ductile materials, which means that even if you apply a force, they can extend without breaking for a longer period of time. So for ductile materials, the distance between D and E is going to be, should be very, very long. All D and E will be much far apart. For brittle, D and E are very close. But D, we have said, is the maximum force or stress a material can withstand before breaking. Now, state what's meant by the yield point of a material. We have mentioned that, so we can now say yield point is the point B, or the yield point. Let's try to give a precise definition there. Stress value beyond which the cable undergoes a sudden plastic deformation. Undergoes a sudden plastic deformation. In part B, we are told the cable and harness are used to accelerate the actor vertically off the ground. Explain why the forces acting on the actor causes him to accelerate upwards. So remember, an object will only accelerate if there is a resultant force. That is according to Newton's second law of motion. So this force tension is going to cause this person to accelerate because the tension force on the cable is acting upward and is actually greater than the weight of the actor. Now then it means that since the tension is greater than the weight, then it means there is a resultant force, and this resultant force is going to be acting upward, which will make the person to accelerate upward. Object will only accelerate if there is a resultant force, and they will accelerate towards where the resultant force is acting. We move to Roman 2. The actor has a mass of 77 kg and is lifted vertically from the ground with an acceleration of 2.1 meter per second square. Show that the tension in the cable is about 920 newtons. So how are we going to go about this? We know that the resultant force is going to be tension minus the weight of the actor. So we can also work out the resultant force using the formula force equals to ma, mass times acceleration. So we can be able to use the mass that we were given and also the acceleration that was given, work out the resultant force. Now we also need to use the formula weight equals to mg, which means that we can be able to work out the weight of this person, which is going to translate to 755.4 newtons. Then now we can be able to use this formula and try to rearrange it in order to find the tension force. So tension is going to be 161.7 plus 755.4 newton. So we add the two. Tension is approximately 917.1 newton, which is approximately 920 newton as it was mentioned there. To make sure the actor is safe, the stress in the cable must be less than 15% of the yield point stress. We are told that the cable has a yield stress of 5 2 2.5. We are told that the cable has a yield point stress of 2.5 times 10 raised power 8 pascals, and the diameter is 7.6 times 10 raised power negative 3 meters. Deduce whether this is safe to lift the actor with the acceleration of 2.1. Now, to work out this question, what we are going to do first is to work out the stress of the cable. And of course, for us to work out stress, we need to know the cross-section area. So let us start by writing the formula. For stress. Stress of the cable is force over the cross-section area, but area is going to be pi over times d over 2 squared, which will mean that we can be able to always check whether the diameter is given in meters so that you can be able to get correct, because if you don't convert the units to meters, you're gonna get it wrong somewhere. So working out the stress, we can be able to find our value as what? Do we have the force? We have the force, tension force, which was 917 divided by the cross-section area. So we get the stress being equivalent to that. Now, we have gotten our stress being equivalent to 2.02 times 10 raised power 7 pascals. So we want to know, we are told that the stress of the cable must be less than 15% of the yield point stress. And the yield point stress was given as 2.5 times 10 raised power 8. So we're going to find the percentage of this in comparison with the yield point stress. So I can say now, using that, divide by the yield point stress times 100. This translates to 8 point something. This translates to 8.08%, and this is actually less than 15%. So which means that is still suitable, is still safe. Yeah, it's still safe with that acceleration. Still safe for that acceleration. We have part C. We have part C, whereby we're told that the original cable is replaced with a new cable made from a different material. This material has a lower Young's modulus than the material used to make the original cable. The new cable is the same length as the original cable but has a greater diameter. This breaking stress is the same for both cables. Explain how the work done to break the new cable is different from the work done to break the original cable. Assume both materials obey Hooke's law up to the breaking point. So if we try to substitute, you can see the best option there is actually C. C is the correct answer in that case. In question 5 is motion on an inclined plane. So these are some of the questions also you may be asked to work out. So we are told that an object accelerates from rest down a frictionless slope. The object moves a distance of 20 meters and the slope is at an angle of 23 degrees to the horizontal as shown here. Then we can see now the distance covered by the object down the slope is 20 meters. Now, which of the following gives the final speed of the object? Remember, this object started to move from that particular point down the slope from rest. So the initial velocity was 0 meter per second. Now, we need to understand that gravity is actually vertically down like that. So this is G. Then if we can be able to resolve this G along the inclined plane and at normal to the inclined plane like that, this angle is actually 90 degrees. Then this angle we have here is equal to 23 degrees. This theta is equals to 23 degrees. Now, this component of G here is going to be G cos theta, and the component that is down the slope is G sin theta. So anytime you are having inclined plane like this, the component of G that is perpendicular to the plane is G cos theta, and the component of G that is parallel to the inclined plane is G sin theta. So we can be able to find what is the value of the acceleration down the slope. So since we know it's 9.81, we can be able to say the acceleration due down the slope is G is actually 9.81 sine 23 degrees. 23 is the angle of inclination in that case. Now, since we have our acceleration to be G sine 23, which is actually the same as 9.81 sine 23, we can be able to use the Suvart equations of motion in order to work out the final velocity. And the best one we can use is v squared equals to u squared plus 2as. Our acceleration we have obtained there. So we can be able to substitute the values, and remember the object was moving from rest, so the initial velocity was 0. So if we substitute everything that we have in this case, and then let me move this a little bit so that I can be able to have enough space, we can be able to find the square root both sides so that we can be able to find what the value of V is. So the expression for this case is actually C. So you can check also in the description. There's a link that will direct you on how you can be able to resolve different components when you're given a question like that. In the next question here, we are told that the velocity time graph shows the motion of a particle with a constant acceleration P, Q, and R represents the magnitude of each of the areas. Now, which of the following expression gives the total displacement of the particle? Now, when you are given a velocity time graph, something that you need to remember from a velocity time graph, you can be able to work out the acceleration by using the gradient or the slope of that velocity time graph. If you are asked to work out the displacement from a velocity time graph, you need to work out the area under the graph. But now in this case, you see the line is joining from the negative part to the upper part. So the region Q is representing negative displacement. R is a positive displacement. So which will mean that for us to work out the total displacement, we are going to add the two areas, R and Q. But since R is negative, our final answer is going to be R minus Q, which represents the total displacement in this case. So we can be able to say the total displacement of the particle is R minus Q. R minus Q, which is actually D. And the reason as to why we are saying that displacement is represented by the area under the graph, and these are the two areas we're talking about. Q being a negative area, so we can be able to say is R minus Q. Moving to the next question, here we are told a student walks for 6 seconds. The displacement time graph for the student is as shown below. So we are having now a displacement time graph. Which of the row, which row of the table shows the final displacement and the velocity of the student? Now you need to understand, when time is 0, it means that's the initial point. So meaning the student moved some distance to the negative side and then moved from that particular point some distance to the positive side. So we can see now if we moved um, 1 meter down from the starting point and again now moved from that point back to 2 meters up in front of the starting point, then we can now say displacement is a distance from the starting point. So what's the distance from the starting point? This person is going to be 2 meters from the distance from the starting point, right? But velocity can be obtained from the gradient of a displacement time graph. So we can say displacement here is actually going to be 2, and that is 2 meters from where this person started. But we can be able to work out the gradient in order to get the velocity of the person. So the gradient here is going to be rise over run, and we can see now the rise is actually, we can talk of a rise of 2, and the time taken is 4 seconds. So that is going to be 0.5 meter per second as the velocity. And you can see this now, the part that represents that. So from a displacement time graph, you can be able to get the displacement of the object, and also you can be able to get the velocity of the object by finding the gradient. Remember also from velocity time graph, you can be able to work out area under the graph, which represent the displacement of the object. From acceleration time graph, if you work out the area under the graph, it represents the change in velocity. Now we can be able to move to the next question here, which is saying that a student determined the acceleration of free fall g. She measured the time t for a ball bearing to fall from rest through a distance s. She repeated this for a range of values of s. Which row of the table shows the graph that will give a gradient equivalent to g? Now remember, in order to work out this, we can be able to use this formula, s equals to ut plus half gt squared. But since it's falling from rest, it means that initial velocity is 0. So this particular part here is going to run to 0, and we shall remain with s equals to a half gt squared. So this is the formula that can be used to work acceleration in free fall. You can see now we are having s equals to a half gt squared. You can be able to plot a graph of s against t squared, then what you work out the gradient of that graph obtained, which is a straight line graph, which will give you a gradient, and that gradient will be equal to a half g. But now, since in this question we can see s does not stand alone, so we can be able to say if we multiply it by 2 both sides, we can have 2s equals to gt squared. So the graph that can be plotted is 2s against t squared, which will give us a straight line, and the gradient of that, you can see now, is going to be the gravitational acceleration due to gravity. So that is 2s on the y-axis and t squared on the x-axis. So that is part B. Okay. Is moving towards a stop sign at a speed of 25 meters per second. The driver applies the brakes 20 meters before the sign and decelerates uniformly to rest just before the sign. So let us see what we are provided with. In this case, we are provided with initial velocity. We are provided with displacement, which is 20 meters. They are provided with final velocity because it's coming to rest, which is 0 meter per second. Then we are supposed to work out now the car's deceleration, and in that case we can be able to substitute what we have in this question. Substituting into the formula, we can be able to say now this is negative because this car is decelerating, so we can be able to say 0 there, because final velocity is 0. So you can be able to say 2as by just taking it on the other side, it becomes a positive, is 25 squared divided by 2s divided by 2s. So we have this cancelling out, and we shall have our a equals to 25 squared over 2 times 20, which translates to 25 squared over 40. So which expression is giving us that? That expression is C. Now, always whenever you are working out this question, don't simplify to the fullest. Keep on checking the kind of formula or the kind of expression that is given in your answer, so that you can be able to see which is the most appropriate answer to write. Now, an object on the moon falls a vertical distance of 0.32 meters from rest. So meaning the initial velocity at that point is 0, and it takes a time of 0.63 seconds. Which of the following six expressions gives the acceleration due to gravity on the moon in meter per second square? So remember, for us to work out the acceleration, we are going to use the Schubert equations. And in that case, we can be able to say the initial velocity is 0, and the height it falls is 0.32 meters, and the displacement 0.32, yeah, which is in meters. We are told to find acceleration, which is g, and then the time it falls, that height is 0.635. Now we are supposed to use this Schubert equation in order to work it out, but remember initial is 0, so this part here is going to be 0.32 equals to 0, and then equals to a half gt squared. Now try to rearrange the expression that we have. We are going to see our answer is going to translate to C, 2 times 0.32 over 0.63 square. In question number 11, an object moves from rest with uniform acceleration for the time t. But I told you from the previous section that acceleration time graphs, the area under acceleration time graph will tell you the change in velocity. So x represents the correct answer in that case. So we are having this object moving at a horizontal velocity of 7 meters per second. That's the ball. The ball is traveling horizontally at a speed of 7 meters per second, and the ball hits the vertical wall and rebounds along its initial path at the speed of 5 meters per second. The ball has an acceleration of 300 meters per second square while in contact with the wall. Which of the following expression gives the time of contact between the ball and the wall? So you can be able to see here is our wall, and this is actually the ball, which is moving at 7 meters per second. It rebounds back with a velocity of 5 meters per second. Now, what you need to remember, when it rebounds, it's moving in the opposite direction. So we are going to really consider some direction there. So remember, acceleration equals to final velocity minus initial velocity over t. So meaning that acceleration 300 is equals to -5 minus, we are saying -5 because we can consider the direction to the right to be positive, but to the left to be negative. So if the object was moving at 7 meters towards the wall, we can consider that positive, but when it's moving away from the wall at 5 meters per second, we can consider that negative. So -5 is actually the final speed. Initial speed was 7 meters per second because it was approaching the wall. Then so it will be -5 minus 7 over the time t. We can be able to rearrange this and have t equals to -5 minus 7, but you can see -5 minus 7 is going to be a negative, and time can never be negative, so we can be able to change the acceleration to be because we can consider it to be deceleration, and then we say this is negative 300. And the reasons why I've done this, because time cannot be negative, but acceleration can be. So that becomes what? If you work it out, the expression that represent that is A for that case. For that case. Quantities in physics are classified as either vectors or scalar. Which of the following units could only be used for scalar quantity? Now, we see meter per second. Meter per second can represent the unit for speed or velocity. So that is can be scalar or can be vector. Meter per second square represent the unit for acceleration, so which is actually vector. Kg meter per second square, this is actually force. Remember, from force equals to ma, so that's why we are getting that unit form. And d is the unit kg meter per meter square cubic. This is the density unit. So density is a vector. Density is a scalar quantity. So in that case, D is the correct answer. Two objects P and Q are at the same position at time t seconds. The graph shows how the velocity v varies with time for each object. Now we have the representation of the graph there, and remember that the area under the graph of velocity time graph represent the distance or the displacement of the object. Now, which of the following statement describe the position of P and Q at time t, which is 4 seconds? Now, if you look at each of them, we can be able to have some information regarding the motion of this object. Now, A, you are told P and Q are both at the initial position. That is not true, because you can see for Q, there is some area under the graph. So meaning Q has covered some distance. But P is in the initial place, because if you work out the area of the upper part and the area of the lower part, both of them are equal, but one has the opposite sign. So they will cancel out and the displacement will be 0. So which will indicate that the object is at the initial position. Yeah. Yeah, so P and Q are at the same distance from the initial position. That's not true, because for P, it is at the initial position and the area is 0, but for Q, the area is not 0 in that case. So you can be able to say A is not correct, and the reason as to why we have said it's not correct is because area under the graph of the two are not equal, or are not both of them equals to 0. So that statement is not true. This one is not correct because the areas are not equal. Because if we are saying P and Q are in the same distance from the initial position, then the area under the graphs must be equal. If we are saying both of them are the initial position, then it means that area under the graph of the two must be 0, which is not true for A and for B. P is further away from Q. Yeah, P, you can see P is at the initial point. Q is the one that is having some area under the graph. So meaning that that statement is not true, because P is at the starting point or the initial point, but Q has some distance. Then therefore, we can conclude and say that Q is further from the initial position than P, because P is at the initial position, but Q, you can see there is some area under the graph, so it means it's somewhere far from the starting position. So if you are new to Proflan YouTube channel, consider subscribing so that anytime I'm going to upload more tutorials of A-level physics, you'll be notified. See you in the next video.
Hi, my name is Dot Lung. I'm a global social media strategist working with companies around the world. Most people have the
Welcome to another tutorial of Proflan YouTube channel. In this particular video, we're going to have a discussion on some of the important mathematics concepts that you need for you to be able to excel in A-level physics. So we are going to draw a right angle triangle like that. We shall have, this is going to be the vertical component, and then here we shall have a horizontal component. So meaning that if we want to find the vertical component of this force of 5 Newton, let us draw a right angle there. So we shall have a triangle at that given point whose hypotenuse is 5 newtons. But we need to know what is the vertical component of force F.